and is headed for its closest pass to the Sun at the end of October. That's going to be barely inside the orbit of Mars, and then it's going to keep going on its way out of the solar system.
Tonight, 3I Atlas sits 2 astronomical units from the Sun, twice Earth's distance, moving inward at 58 kilometers per second. That speed is more than double the velocity of any planet in our solar system. Mercury, the fastest, orbits at just under 48 kilometers per second. 3I Atlas would cross the gap from Earth to the Moon in a little over an hour, a journey that took Apollo astronauts 3 days. On the astronomical magnitude scale, the comet has reached magnitude 12. The faintest stars visible to the naked eye are around magnitude 6. Each step on this scale represents a significant change. A difference of 5 magnitudes means a 100-fold change in brightness. A jump from magnitude 16 to 12 is a leap of about 40 times in brightness. Yet even at this level, the comet remains invisible to unaided eyes. Only with a mid-sized telescope and clear, dark skies do amateur astronomers catch a glimpse. For most, it is a ghostly smudge, barely distinguishable from background noise. The coma, the glowing envelope that surrounds the nucleus, has expanded to nearly half the diameter of the Sun itself. This is not simply a visual effect. The coma is a real physical structure, hundreds of thousands of kilometers wide, made up of ice and dust, vaporized by the Sun's heat. Estimates for the nucleus size range from a compact 0.3 kilometers to a more substantial 5.6 kilometers across. The nucleus remains hidden, shrouded by the thick cloud of gas and dust. Trajectory calculations confirm that 3I Atlas is following a hyperbolic path. It is not bound to the Sunday. This is a one-time passage through the solar system, never to return. Its closest approach to Earth will be no nearer than 1.8 astronomical units, so there is no danger of impact or debris. The urgency lies elsewhere, in the fleeting opportunity to observe an interstellar visitor as it races through our solar system, soon to vanish into the Sun's glare. Within hours of a brightness spike in late September, the Comet observation database lit up with alerts. Amateur astronomers in Australia posted the first flagged measurements, noting a 6-fold increase in light output over just 2 nights. On October 3rd, 3I Atlas sweeps past Mars at a distance of about 30 million kilometers. Close in cosmic terms, yet still well outside any risk zone for the red planet or its orbiters. As the object barrels inward, the geometry of its path conspires against ground-based astronomers. The angle between the comet and the Sun, known as solar elongation, narrows day by day. By October 21st, this angle dips below 30 degrees, a critical threshold. Below that, even the most advanced telescopes struggle to pick out the comet's faint glow from the overwhelming brightness of the evening sky. For most observers, the practical viewing window closes in early October, just as the comet makes its closest approach to Mars. Perihelion arrives on October 29th or 30th, when 3I Atlas will pass within 1.36 to 1.4 astronomical units of the Sunday. At that moment, its speed peaks near 68 kilometers per second, and its activity is expected to reach a maximum. Yet from Earth, the comet is lost in solar glare, invisible to even the largest observatories. This blackout period, spanning from early October through early November, means that the most dramatic phase of the comet's evolution will unfold beyond the reach of direct human eyes. The handoff begins with a scramble. Observatory schedulers across the globe find themselves in a race against time and against the Sunday. With the comet's light curve veering sharply upward, major facilities activate target of opportunity protocols. The Hubble Space Telescope, already oversubscribed, carves out an emergency imaging slot, capturing ultraviolet and optical frames as the coma balloons. Each Hubble exposure has to balance the risk of saturation against the need for detail, with instrument teams recalibrating on the fly to keep pace with the comet's rapid brightening. The James Webb Space Telescope secures a rare committee-approved window for mid-infrared spectroscopy. On August 6th, the NIRSPEC instrument locks onto the coma, registering an unusually high carbon dioxide to water ratio, about 7.6, far above the norm for solar system comets. This finding, flagged in real time to the Minor Planet Center and shared in private coordination channels, sets off a wave of requests for additional spectral coverage. Gemini South Observatory, operating out of Chile, pivots next, grabbing a sequence of optical and near-infrared snapshots. Gemini's wide field and fast switching allow teams to monitor subtle changes in coma structure and color, even as the object's brightness fluctuates from night to night. Each facility brings its own strengths and its own constraints. Hubble can resolve fine coma features, but only in narrow time slots. Webb delivers unmatched sensitivity in the infrared infrared, but scheduling is tight with other high-priority targets queued up for the same window. Gemini's ground-based vantage is limited by weather and the comet's shrinking solar elongation. Coordinating these assets requires choreography, more common in planetary defense exercises than routine comet work. Observatory directors juggle requests from competing science teams while data pipelines run overnight to process and distribute raw frames. The sense of urgency is sharpened by the approaching blackout. Once the comet slips into the sun's glare, Earth-based telescopes will be blind for weeks. The last usable datasets, Hubble's ultraviolet images, Webb's carbon dioxide spectra, Gemini's color snapshots, will serve as the final record from Earth's perspective. Mars becomes the solar system's best observatory when Earth's instruments are blinded by the sunday. Orbiters circling the red planet are suddenly tasked with tracking a comet that was not part of anyone's original plan. Each spacecraft brings a specialized set of tools, and teams of engineers and scientists scramble to adapt, reprogramming instruments and negotiating precious observation slots. High-resolution imaging science experiment, known as HIROS, on NASA's Mars Reconnaissance Orbiter, is known for its ability to resolve objects as small as a desk from orbit. With a 0.3 meter per pixel resolution, HIROS can, in theory, spot the nucleus of 3I Atlas if the background glare and tracking geometry cooperate. But tracking a comet moving at 58 kilometers per second, millions of kilometers away, stretches both hardware and software to their limits. Teams at the University of Arizona and the Jet Propulsion Laboratory run simulations, tweak exposure times, and fight for imaging windows. The risk is not just missing the comet, but overexposing the camera or damaging pixels if the sun creeps into view. The European Space Agency's Mars Express, orbiting since 2003, brings the high-resolution stereo camera. This camera excels at wide-field multi-angle imaging, ideal for capturing the full sweep of a comet's coma and tail. Its color filters help separate dust from gas, while stereo pairs may reveal subtle three-dimensional structure in the expanding cloud. The operations team in Germany coordinates with ground-based astronomers to time exposures for when 3I Atlas passes closest to Mars's orbital plane. The ExoMars Trace Gas Orbiter carries CASIS, the color and stereo surface imaging system, and NOMAD, a suite of spectrometers built to detect faint atmospheric gases. CASIS, designed for Martian geology, can be retasked to image the comet's coma in multiple color bands. Its rapid imaging allows tracking of changes in brightness and structure during a single flyby. NOMAD is optimized for detecting trace gases like carbon dioxide, water, and rare organics. By aiming its spectrometers at 3I Atlas, the team hopes to confirm the elevated carbon dioxide levels first flagged by Webb and search for chemical signatures never seen in solar system comets. NASA's MAVEN mission joins with a different perspective. Its imaging ultraviolet spectrograph tunes into emissions from atomic oxygen and carbon, while plasma instruments measure how the solar wind interacts with the comet's outflow. MAVEN's data could reveal whether the coma's green glow is driven by atomic oxygen or more exotic processes. Its orbit, designed to sample Mars's upper atmosphere, puts it in a prime spot to catch the comet's passage from multiple angles. Mission operations centers in the United States and Europe run emergency meetings, weighing the risks of diverting instruments from routine Mars science. Every observation slot is a negotiation among engineers, principal investigators, and project managers. Safety protocols are strict. Cameras must avoid direct sunlight. Spectrometers need careful calibration, and dust hazard models must be checked. Sometimes software patches are uploaded at the last minute to enable new tracking modes or override default safety limits. No single orbiter can capture the full story of 3I Atlas. Together, this international lineup forms a synthetic observatory, stitching together imaging, spectroscopy, and plasma measurements across orbits and time zones. As Earth's view fades, the responsibility for decoding an interstellar visitor passes to these robotic eyes at Mars, each one poised to gather data that could reshape our understanding of comets and the chemistry of objects from beyond the solar system. The first anomaly appeared in the brightness record, not the slow rise and fall typical of comets warming as they approach the sun, but pulses, sharp spikes in light output arriving at regular intervals, each one lasting hours before fading back to baseline. The pattern held across multiple observation runs, confirmed by amateur networks in Australia and professional arrays in Chile. The timing was too clean for random outgassing. Gas jets from a tumbling nucleus create irregular flares, not metronome precision. Spectroscopy brought the second surprise. Instead of familiar water vapor lines dominating the spectrum, spectrum, carbon dioxide signatures towered over everything else. The carbon dioxide to water ratio topped 7.6 to 1 in Webb's mid-infrared data, an order of magnitude above the most volatile rich comets on record. This chemical fingerprint is so rare that laboratory models struggle to match it. Solar system comets form in regions where water ice dominates. Carbon dioxide plays a supporting role. 3I Atlas flips that script. The coma glows emerald green, peaking at 516 nanometers. The color persists across instruments, confirmed by both ground-based and orbital spectrographs. Traditionally, green comets owe their color to diatomic carbon, which fluoresces in the swan bands near 510 nanometers when struck by sunlight. Yet, as spectroscopists pored over data from Gemini, the Very Large Telescope, and Webb, the expected diatomic carbon emission lines were nowhere to be found. No swan bands, no hint of the classic carbon signature, even as the coma's brightness intensified. Instead, the spectra pointed to a different source: atomic oxygen, specifically the forbidden oxygen, one emission at 5,577 angstroms. This green line appears when sunlight and energetic electrons break apart carbon dioxide and water molecules, freeing oxygen atoms that emit green photons as they relax from a metastable state. In the dense carbon dioxide-rich coma of 3I Atlas, solar, ultraviolet, and photoelectrons act as catalysts, turning the region into a factory for green atomic oxygen emission. Nickel emission lines, especially at 337 and 380 nanometers, outshine iron by factors of 4 or more, a reversal of what is seen in every known solar system comet. Imaging and polarimetry add another layer. The coma's green light is matched by a deep negative polarization branch, a trait more common to certain asteroids than to icy wanderers. Dust tails reveal grains larger and slower than standard comet dust, with trajectories that resist easy modeling. These grains drift in a broad, lazy arc, as if released by a mechanism that doses out mass in measured bursts, not chaotic jets. Astrometric tracking records micro-accelerations, tiny course corrections that do not line up with any known outgassing profile. Each nudge coincides with a brightness pulse, suggesting a link between light and motion. The data are checked, cross-referenced, and rechecked. Telescope pointing errors are ruled out. Atmospheric distortion is accounted for. The accelerations remain small, but statistically significant. Repeating, no single anomaly stands alone, but together they sketch a portrait of an object that resists every simple category. The question is not whether 3I Atlas is strange. The question is whether the strangeness fits within the boundaries of known physics or demands something new. Most planetary scientists start with the simplest tools at hand: physics and chemistry. 4 main hypotheses have been tested against the growing dossier of anomalies. The first points to chemistry shaped in the deepest cold. In this view, 3I Atlas formed far from any star, where water freezes out and carbon dioxide, carbon monoxide, and even rarer ices dominate. Comets from the Oort cloud hint at this kind of chemistry, but none have shown a carbon dioxide to water ratio so extreme. Still, interstellar space is vast, and our catalog is tiny. A single outlier could rewrite the boundaries of comet chemistry. The second model turns to structure. Volatile pockets, deep reservoirs of trapped gases, could erupt as sunlight seeps through the crust. These pockets, if distributed unevenly, might explain the rhythmic pulses in brightness. Laboratory simulations show that even small temperature differences can trigger sudden jets, sometimes repeating if the layers are stratified. Regularity, though rare, is not impossible in a body shaped by billions of years of cosmic weathering. Dust dynamics offer a third explanation. The coma's emerald glow and the presence of large, slow-moving grains could result from unusual dust composition or size distribution. Solar wind and Mars's weak magnetic field might shape the tail, herding charged grains into broad arcs. Models of comet tails show that in certain geometries, heavy grains lag behind, drifting in lazy curves that mimic measured bursts. The negative polarization branch, more typical of asteroids, could hint at compact carbon-rich grains rather than icy fluff. Finally, some point to the limits of the models themselves. With only 2 previous interstellar visitors on record, every new arrival tests the edges of simulation. Micro-accelerations and synchronized pulses may reflect physics not yet captured in software. Subtle interactions between sunlight, volatile release, and tumbling motion. In this view, the anomalies are not evidence of intent, but reminders of how much remains uncharted. For each puzzle, the scientific community demands that every natural explanation be exhausted before considering anything more exotic. The bar is high. It has to be. Extraordinary claims require extraordinary evidence, and the process of verification identification is deliberately slow. Every candidate event flagged by one instrument must be confirmed by another. A spike in particle flux has to match a twist in the magnetic field or a change in the coma. A spectral oddity has to echo in a different detector. Only convergence can turn a candidate into a confirmed anomaly. On October 3rd, as 3I Atlas passes within 30 million kilometers of Mars, every major orbiter and rover turns its full attention to the sky. The observation window is narrow, 6 hours. Earth is on the wrong side of the sun, communications delayed, viewing geometry poor. Mars becomes the only platform with a clear line of sight. The data that stream back over the following 40 hours will either fit the natural models or force them to expand. MAVEN's imaging ultraviolet spectrograph sweeps the coma, searching for faint emissions that betray hidden chemistry and sudden outbursts. Its magnetometer and particle counters ride the thin boundary of the Martian ionosphere, listening for ripples that might mean charged dust or plasma is interacting with the planet's environment. Mars Express captures overlapping images every few minutes, stacking them to pull structure from darkness. The SpyCam spectrometer slides across wavelengths, hunting for familiar fingerprints and unfamiliar ones that refuse assignment. The trace gas orbiters NOMAD and ACS spectrometers probe the coma for trace gases, hunting for isotopic ratios or molecular fingerprints that defy solar system norms. CASIS attempts to catch fragmentation events or dust jets in progress. Each spacecraft runs on a script rehearsed until it feels automatic. Every command is logged, every data packet gets a redundant copy. On the surface, Perseverance and Zhurong contribute quietly. Their air sensors watch for unfamiliar dust. Their cameras wait for faint auroral curtains. Their role is not headline making, it is insurance. If something unusual brushes the thin Martian air and the orbiters miss it, the rovers might still catch a trace. The data begins streaming back. The emerald coma holds steady. Brightness pulses arrive with timing so clean it looks like machine code laid across the sky. MAVEN sees faint ionospheric ripples rise exactly when the light spikes. Mars Express records subtle shifts in coma shape that align with those same spikes. The tracking logs show micro-accelerations arriving like echoes after each brightening. Tiny, precise, repeating. The trace gas orbiter reports chemistry that raises questions. Carbon dioxide signatures tower over water. Nickel lines outshine iron by wide margins. The isotopes are checked and rechecked. Carbon ratios look slightly off-center for solar system material. Not wildly alien, just enough to make a careful analyst sit up straighter and ask for more runs before saying anything in public. The room does not erupt in cheers, it tightens. Each anomaly needs a partner before it moves from candidate to confirmed. The ripples have Mars Express shape changes. The micro-accelerations have tracking confirmations. The chemistry has independent readings from 2 spectrometers. The picture that forms is not clean, but it is consistent in a way that demands attention. Over the next 40 hours, data bore home. What the orbiters see does not answer every question, but it hardens the bones of the story. The emerald coma at 516 nanometers stays stubborn and bright. The rhythmic pulses are clockwork, with onsets and decays that look engineered even to people who dislike that word. The carbon dioxide to water ratio remains 7.6 to 1, a number that does not live comfortably in the world of ordinary comets. Nickel over iron refuses to budge. Dust motion traces wide arcs, as if released in patient handfuls. Natural models rise to meet the challenge. If you push formation conditions to the far edge of cold and isolate bodies in deep interstellar space, it is possible to design scenarios where water freezes out and carbon dioxide dominates. If you layer volatile pockets under a tough crust and spin the body just right, you can create repeating vents that mimic a metronome. If you choose grain sizes and compositions with care, you can tilt scattered light toward green and pull the polarization in a direction more common in carbon-rich asteroids. All of those ideas live inside physics and chemistry. None of them explain the tiny course corrections marching in time the light. That synchronization is the needle that will not pull free. Random gas jets shove. They do not steer with millisecond timing. If light pulses and path nudges travel in lockstep again and again, there are only 3 families of explanation. 1. We are watching a natural feedback loop we do not understand, where heat, rotation, and buried volatiles couple in a way our models do not capture. 2. We are measuring something else entirely, like solar radiation pressure or magnetized dust, and misreading it as steering. 3. There is intention. The decision matrix set a high bar. At least 2 independent anomalies, statistically strong, confirmed by separate platforms. The data tick several boxes but do not lock the door behind them. The pulses and the nudges are cross-confirmed. The chemistry is cross-confirmed. The color and dust behavior behavior are cross-confirmed. The isotopes tug at the sleeve of the conclusion without ripping it off. In plain language, the evidence says this: 3I Atlas is not a normal comet. It may be a type of comet we have never seen. It may be a natural object doing unnatural-looking things. Or it may be something that carries a design we cannot yet read. The verdict remains open. As perihelion approaches on October 29th, the comet will round the sun at maximum speed and maximum activity, invisible from Earth, monitored only by solar observatories, and whatever Mars assets can still track it through the glare. Models predict 3 outcomes: a slow fade as volatiles are spent, a final flare triggered by fresh pockets of carbon dioxide, or sudden collapse, or disintegration, the nucleus breaking apart under solar stress. Each outcome feeds data back into the models. A smooth decline in brightness hints at simple outgassing. Erratic jumps or sudden drops could signal fragmentation. A persistent green coma after perihelion would point to deep stores of carbon dioxide-rich ice. A rapid color shift back to red or blue might reveal the exhaustion of those volatile layers. The Mars flyby and perihelion window create a rare laboratory, one where predictions can be scored against real events, and where the boundaries between the known and the possible are tested in real time. Key milestones are already marked. Mars orbiter data releases in early October, perihelion on October 29th and 30th, the return of Earth-based views in November. The story of 3I Atlas is a live experiment unfolding at interstellar speed, with every new observation a chance to glimpse the physics of worlds beyond our own. Even with the best instruments, some cosmic visitors leave more questions than answers. The next weeks will decide which models hold up and which must be rewritten.